Welcome to the Polycast. My name is Sil. Bienvenue au Polycast, le podcast de Polytech Montpellier, l'école d'ingénieurs de l'Université de Montpellier. Le Polycast reçoit des invités de tous les coins du monde et de tous les horizons professionnels, qu'ils ou elles soient scientifiques ou littéraires, artistes ou businessmen, penseurs, penseuses, acteurs, actrices de terrain. Nos invités nous aident à mieux penser la société. Leur expérience éclaire la nôtre. La prolifération de nos outils électroniques, smartphones, tablettes, PC, et l'utilisation que nous en faisons ont été amplifiées récemment par la pandémie du coronavirus. Elles le seront plus encore avec le déploiement de la 5G. Cette croissance exponentielle des outils technologiques et de la masse d'informations qu'ils stockent et véhiculent ont un coût environnemental monumental, mais le plus souvent ignoré, hélas. L'énergie nécessaire à la production et l'utilisation de ces outils, mais aussi les déchets qu'elles génèrent, sont des sujets qui inquiètent vivement tous ceux qui réfléchissent à cet impact environnemental. Notre invitée du jour, Aida Todri-Sanial, elle réfléchit beaucoup, bien sûr, mais aussi elle agit. Directrice de recherche au CNRS, au sein du LIRMM à Montpellier, Aida Todri-Sanial est spécialiste en nanoélectronique. Avec son équipe, elle étudie les connexions neuronales et synaptiques du cerveau humain pour en reproduire l'efficacité et modéliser des composants électroniques moins gourmands en énergie. Ses nombreux travaux scientifiques servent également à étayer son lobbying auprès d'instances européennes pour acter l'urgence de réduire notre consommation d'énergie et la pollution qui en découle. Diplômée de UC Santa Barbara, Aida vit en France depuis 10 ans. Elle travaille en anglais et donc notre conversation est en anglais. Et maintenant, voici le Polycast d'Aida Todri-Sanial. Aida, welcome.
Thank you for having me.
Well, thank you. It's a real pleasure. I need to probably give a shout out to our mutual friend, Lionel Torres, director of Polytech Montpellier, who basically put us back in contact. I mean, we crossed paths, but your colleagues at LIRMM, is that correct?
Yes. We are in the same department here at LIRMM, in the microelectronics department.
Excellent. Cool. Well, I'm super glad to have you on board because we have a bunch of electronic students at Polytech, and I'm really excited about asking you some questions which are going to impact how they may think about electronics in the future. But before we go into what you do specifically, can you give us like a general sense of, well, you know, your background, but how you got to where you are now? You know, I should probably say that I prefaced this interview with a little introduction explaining what you do and who you are, but it's better if we hear it from you.
Okay. So I don't know how far back I should start, but maybe I should start with my graduate studies. So I have a PhD from UC Santa Barbara on computer and electrical engineering. And during my PhD studies, which is very common in US, you have a lot of summer jobs. So where you kind of get to have a little bit of an industry experience. So I got to work throughout each summer during my graduate studies, and I had the opportunity to work for various high-tech companies like as ST, Mental Graphics, and then also IBM for 2 years in a row. So it allowed me to have a little bit of both an academic and industry experience. So after my PhD, I started working for a national governmental lab in US, so Fermilab, which is in Chicago, in Illinois. And after some of that work experience, I moved to France, where I joined CNRS. And I started as a junior researcher, and then over the years, now I'm a director of research, and I have built my research team and also my projects on various topics related to physical design. So focusing from devices, circuits to architecture. And the main core of all of this research is the power consumption. So that is also the common denominator through my PhD and my research now, is to this quest toward how can we build energy efficient electronic system, looking from the devices, circuits, all the way to architecture. So that, in a sense, has been my journey, both academic and industry, and now with CNRS and also with my current team.
So that's very, it seems very, you know, streamlined, but how do you go from, you know, doing electronic studies to suddenly saying, you know, I have to look for efficiency. This is what I want to go for it. This is what drives me. How do you go from generic electronics to saying, look, it can't be that energy hungry. This is what I got to work on. How do you point to that?
So indeed, it is a journey, right? So it doesn't come, it's not something that comes up or pops up overnight. It's something that I have to say that my research is driven a lot by my curiosity. So if I were to say one thing as well on my personal side of, academic research is that I've always been curious how things worked and what made them work. And also because we cannot see the nanoscale, I was always very curious what happens at the nanoscale. So that has been sort of trying to interlink what happens between the physical mechanism and what happens in the electronics. And that was also my PhD topic, in a sense, to understand what is the power consumption on an electronic system, more specifically the microprocessors, which is the core of an electronic system, and how can we improve this power consumption? So what are some of the design methods, some design tricks? So in the end, it was a lot about understanding the underlying physics, coming up with design methods toward a better or more efficient design.
Was that Ida, was that an environmental pursuit early, or was it just merely, okay, so devices have to be just thinner, lighter, and consume less energy? Was it more like an efficiency quest more than an environmental search? Because I know now you're involved in that, and we'll talk about it.
Yeah.
Did you immediately say, I got to do this because we can't have all those electronics using all that energy, or you came to it gradually?
Yeah, so very good question. It came in the beginning was more of a tough mathematical problem that I would like to address, right? So in the end, you need to design, but it has to be some optimization. So some initially started with a mathematical formulation and a problem that I wanted to tackle. And then throughout the years, when you see, the electronics now, and especially, who doesn't own several of, high-tech devices, from phones, computers, laptops, iPads, you name it. So it became even more, when you do the math to figure out what is the impact in terms of what is the power consumption, you figure out that is the number one challenge with our devices. It's not necessarily the better, the faster, the most good looking, it's the power. And this is the unspoken problem. And so it kind of hit me over the years also, when we are trying to make our research a little bit more, how to say, attractive, but also for people to know, to bring awareness. And I realized that this was it didn't belong only to my scientific sort of group and our community. It belonged to everybody. People need to know about this. And now it also has become a momentum. We have built some momentum because it requires the awareness of, not only from us, as I mentioned, as scientists, but from all levels. And it starts from students. Students need to think about what is the design they're building. Even if they are building their little analog or digital block, they need to ask the question, how this is going to perform and what is the power required with it. We cannot anymore sort of take it for granted. There's not abundance, and we need to think about also how to harvest energy, but also renewable energy.
So let's maybe, and we'll go back to the American part of your background, because you and I share that, and we've exchanged on how culturally there are things we would like to see here that we don't see, and we're trying to move them to happen. We'll go back to that later. Let's just dive right into what you're working on. So the problem, as you see it, is a proliferation of devices, right? And the fact that they consume tons of energy, and they also produce e-waste, right? And so you're working, as I understand it, on ways at the nanoscale to use fewer components and less energy, so that these things are lighter and produce less waste. That's the one thing. And to do that, if I understand this correctly, you're modeling the brain, the human brain, to see what happens, because you feel it's very, very efficient in its operation modes. And therefore, if we're able to model it and replicate what's going on, then we may be able to have super fast, super lean electronics. Is that what's going on?
That's right. You did a very good summary. So if I were to classify it, it would be as exactly three main parts. So the first one is on the materials, on the physical properties of these materials. So as you mentioned, we need energy efficient. So where does it come from? It comes from the choice of our materials. We not only need good materials with physical properties that will allow us energy efficient, but we also want materials that are less toxic or hazardous, because we need to think about their life cycle, how we recycle them, what happens to them after 3-5 years that we use them. So we want materials that are indeed thin, compact, that have suitable physical properties such as carbon nanotubes or 2D materials. They have this very high mobility of electrons. That means electrons flow on these materials very fast. So they don't bounce back and forth. Think like a ball that just goes straight through rather than scattering, bouncing around. Anything that when electron starts to bounce, it creates a lot of parasitics or resistance, and it's a waste of energy. So for that reason, we want materials where these electrons have a very high mobility and ballistic. That means straight through. So that's why carbon nanotubes, using them as the building block or the channel for devices, so field effect transistors, we have shown that we have better performance. That means that they switch faster. We can compute faster with them. Also with 2D materials. So this is very interesting. So that is the first pillar. The second pillar is, can we architect, so now we have these materials, what can we do with them? So using the same classical convention, so architectures, it's a little bit limiting, because in the end we'll come to the same challenges that we are having with classical computers. What is the main challenge on classical computers is that we have a memory and a processor, and then we have this data bus in between. And this data bus, it limits the bandwidth, how much data can flow. It limits also the power or the exchanges between a memory and processor. So we need to think about something like computing in memory, something that is a more hybrid. And what allows that, this is why we took inspiration from the brain, because the brain is an interconnected system. It's a neural network of oscillators, of neurons that could act as oscillators because of their wave or their frequency in terms of the given brain waves, and they can have different frequencies. So to look a little bit into the brain as a model to build architectures that are energy efficient. So you need the right devices, the right materials, and the correct architecture in a sense that is hybrid. So it's not like a von Neumann, so you have separate processing with memory. So that's why there is this quest that brain-inspired or neuromorphic computing could address this challenge of energy efficiency, especially now that we need to deploy it in very large numbers, with a growing number of population, with a growing number of electronics. So the neuromorphic computing could be the potential to address this problem.
So do you work with materials engineers and doctors as well to do this, or are you yourself involved in the actual physical part of designing those systems?
So this is an ecosystem, right? So I am part of the puzzle, but this is an ecosystem of scientists. So I collaborate very closely with people in the clean room that develop some of these devices, grow these materials, because these materials are not sort of streamlined yet. So we need to have very special process line of how to grow them, the high quality. And also I collaborate a lot at the European level on various projects with the researchers, from Germany, Switzerland, so IBM, Fraunhofer, other academics and industry, to be able to have a very good characterization of these devices as well at the system level. So it doesn't remain device only understanding, but also at the system level. And with respect to the neuroscience, yes, indeed, we do collaborate a lot with neuroscientists to understand a little bit better what are some of the learning modes of the brain. So for example, as I mentioned, we want to get these neurons to represent them as some brain frequencies, or like oscillating frequencies. Then that's where we collaborate with neuroscientists. We need to learn also how can we apply these neuroscientific approaches or understandings into electronics. So there is a bridge, right? So there is a lot of understanding from biology, from neuroscience, but emulating them into electronics, now that's a really another challenge on its own, because what would be the devices to represent? So there is a turn now into analog computing, because a lot of these biological functions, we are representing them as analog functions or as analog blocks. So that's why I would make a shout out to the students in the electronic department there at Polytech. To analog is something that allows a lot of creativity, allows a lot of customization, and also allows to think about performance and power at the same time. So you are not limited into the digital blocks as we have in the digital design. So that's why a lot of this neuroscientific, as I mentioned, approaches, we are looking into analog design representation. And that's where a lot of the fun starts, because now creativity is the only limit, or the sky is the limit, right? Because this is where you understand the theoretical, some theoretical concepts, and representing them, what it is going to be like in electronics. So that's where it's a lot of fun, because now we can think. Now we can, be a little bit creative of how we design, and that's where a lot of fun, also for me and the students. So I always find myself that I'm a student, and I'm always having fun or learning with my students and my colleagues on these various collaborations. So it's very exciting.
You've got to keep learning all the time. That's for sure.
Right. That's right. That's also the motto. You got to keep learning, got to keep asking questions, and be curious.
So a few questions come to mind. First of all, I'm thinking you have a bunch of disciplines in the work you do, from materials to software to electrical engineering, I guess, and electronics. Because I'm thinking of all our students that could be interested in this type of research. It is really an intersection of a lot of disciplines. Is it not? And in your team, do you have a whole bunch of different profiles? What is your team made up of?
That's right. Also in my team, I try to get students, postdocs and PhDs that are actually complementary to my skills, because that's where also a lot of the learning comes, right? So you'll see in my team that I have postdocs that come from atomistic simulation that allows to perform atomic level simulation. So like first principles simulation. And that's very exciting, because you actually see things that you don't necessarily see at the design level simulation. So it allows you to get an understanding. What if I were to use this material with this material? What would be the interface? What would be the electron flow? Does this combination is a better one? So it allows us to get a lot of insights. And with these insights, we can go further. So now we can customize the design of the device. So we can optimize, for example, what's the right geometry, how to connect them, or if we connect them this way. So the architecture questions come in. So there's a lot of what if. So if you look into my students, so there is atomistic, then there is the device modeling people. So there's a lot of modeling and simulation. There are also PhD postdoc students in the clean room, so in terms of the device development. And then there is all to architecture, right? To architecture in terms of a system level. So in the system level, we have different criteria or different things to take care of. For example, is the bandwidth, or is the interface? How would you do the readout? So there is a little different constraint. So it's a more system level. And now we can talk about scalability. How big of a system can we build? What is the performances we can get out of it? And the power as well. So there's a lot of design, so the layout, the schematic, but also toward the tape out if we were to build a real chip. So in the Neuron, so it's one of the projects, and if I make a shout out to one of the projects, the idea here is to build this neuromorphic chip. So we go from, as I mentioned, from atomistic simulation, device development, to architecture, to develop this neuromorphic chip, which can do inference, or can do learning at the edge. So if you were to be deployed, for example, for artificial intelligence, that means it's very power sufficient. So this is the whole path. So if I look at the whole team, they all have complementary skills. And this is also the fun of being in a team. In a team now, for me, is we can go further together. That means a single person can go so far, but when you have this many more brains, intelligent people around you, you can go so much further. And it's so it's not only a scientific journey, it's also a human journey, because we are, you are evolving, you are learning along the way.
That's right. And I'll go back to the management of your team a little bit later when we talk about women in science as well, because I know you have been able to have many women in your team. Going back to the scientific part of this discussion, though, Ida, one of the things I ask my researcher friends every time I speak about their work with them is, how far are you from a bridge towards something that I can use? How far in time? How far physically? Are you doing fundamental research only, or are you doing stuff in the lab, in a clean room, that is actually physical, where you can materialize part of your research? Or is it completely removed from reality for now? So the question goes to you too and your team. You know, how far are you from a real product that we could use at a nanoscale, or things that would be immensely less power hungry based on your models?
A very good question, and very pertinent as well, because we need to think about how to transport our ideas from lab to more real applications, what we call this lab to fab, how this can be going to more real applications, prototypes can be deployed. So I have to say that our research is a little bit, so it's emerging, so it's not immediate or near term. It's a little bit more middle to long term, because we are working on some new computing paradigms, also new materials that are not streamlined on the process, on the manufacturing process lines. So if we were to use the conventional processing methods, indeed, that would make it easier for us to be adopted by industry and to go towards some prototyping. But this is the beauty of the European projects. It allows us for 3 to 4 years to work from concept always to some mature level product or prototype that shows what is the interest or the added value, why it is competitive, what problem does it address. So I'm doing this in terms of 2 projects at the moment. So as I mentioned, Neuron, but also Smart Vista, where the idea is to go beyond just science, so just fundamental science, but towards something that can be of interest and people can adopt it, either technology adaptation or maybe toward a creation of new products based on this new technology. So indeed, the focus now, it doesn't remain only sort of in a closed community only between fundamental scientists, but it goes toward real applications. And on both projects, there is real applications behind that is driving the technology need. So it is an application-oriented technology development, but it's not necessarily in 3 years. So I would say it's in more midterm to long term, because indeed the risks, the breakthroughs are there, but also the risks associated with this new technology are also enormous in terms to overcome. So there is a lot of trade-off.
Can you, okay, you said mid to long term. Can you quantify that?
Yeah, so by end of the project, so at least in 3 to 5 years, so in 5 years, we would like to have a chip that as I mentioned, a neuromorphic chip that people can start to play with it to see what would be their advantage in terms of energy. And I'm also currently working with a startup in Paris, so AI Emergence, who is actually interested on using this type of neuromorphic chip for doing inference, live real-time inference. So it is an ongoing sort of, we are not separate, right? So the ecosystem is also with this end user in mind. And in the Smart Vista, we are also working with medical equipment type of companies, because the system that we are building, so this is real-time monitoring, health monitoring type of a system that we are developing, and that he might be the end user. So there is a lot of technology development at the moment, because this is where we want to show the need or sort of the improvement factor. But there is, this end user in mind, the application in mind, and we hope that in 3 to 5 years from now, we have a working prototype that people could start to play with and give us feedback, because we also need this feedback in order to what to further improve. So it doesn't remain a closed circle between us. So these are very pertinent questions, and even now more and more the European funding agencies and also in France are much targeting to, okay, what problem are you solving? What type of application you're trying to also demonstrate that there is an added value. So there is a lot of, it has to serve for something, and we need to think, whatever we develop, we need to think the power consumption, the type of materials we use, because we need to think of lifetime as well, reliability and lifetime of this system. So it's that's why it takes several years, and it takes a lot of efforts, manpower efforts toward this to achieve such goals.
So here comes a tough question then. One, don't you think that all these awesome efforts, and I'm thinking also of, and I don't know, you may be able to talk about that, the efforts of Elon Musk with Neuralink, his brain-machine interface company. And he's trying to say, okay, within 2 years, I'll probably have some kind of rudimentary interface with a human brain. If he gets FDA approval, that's another question. But we know Elon drives things really hard and he pushes super hard. And we in Europe are probably slower and more cautious, legitimately so. And perhaps the Chinese are way ahead of us in this field because they don't say everything they do. But so the question really for me is, do you think that by the time you're able to have a really working system that's really efficient in terms of energy, it won't be too late in terms of, because devices are proliferating. Yeah. And so the idea that you're trying to address, which is, it eats too much energy and we're creating junk that we throw away all the time. Let me fix it by making it less power hungry. Aren't you afraid that we're not going to make it? That all these efforts, yours and many other efforts to make things that are less power hungry and more efficient are not going to be finished in time for us to survive, really.
To act on it.
I know it's a huge question. It's a lot of responsibility on your shoulders, Aida.
Yeah. So, but let me point first on Elon Musk. So, yeah, he's the guy that has a lot of innovative ideas. So we have to give credit because he wants to take people to Mars. He wants to build the Hyperloop. So LA, San Francisco. He wants to, he has the most efficient cars out there, and also this new chip, in terms to stimulate the brain directly. So it's very exciting. We need this kind of people to drive the new ideas and technology. And indeed, it took him, decades. So this is also something, but at least the first steps are made now, right? So maybe this Neuralink first chip, we'll see that there will be challenges at first. So there is a lot of, the process is ongoing, right? So also for us, we are trying for a very niche type of applications, so embedded intelligence, right? We want to provide this low power solution. Indeed, we will not be able to target maybe all electronics, but at least for very niche, especially in the coming of 5G, where there is a lot of embedded AI everywhere. This is where I think we can have an impact. So I'm very optimistic. It does take, so research, as you know, there is cycles, phases into it. But there is always this continuing progress. And I believe that we need to, yes, maybe we are a little bit late to start to target the problem, but at least there is a lot of effort, Europe-wise, world-wise, in terms to how to mitigate a lot of this power consumption, but also how to look into various different design methods. So I have to say that I remain very optimistic because research is always in progress. But at least we will try to see how we are, in the coming of AI and embedded AI, how we are actually, how we are addressing this problem and how we are making an impact. So I strongly believe that things will not come research is a long-term investment. You know that as well.
Yeah.
Results don't come over, even a year is short at times in terms of research lifetime. So we need this investment on research now. So maybe this is also a call for whoever is listening from the main institutions, that we need to invest more in research, and we need new ideas. We need people that are fierce, people that have this creativity spark on them.
Yeah, and we're going to go back to this. We're going to spend time on thinking out of the box, because it's something that both you and I like to talk about. I have one more question on your research, and I forget the exact word for this phenomenon in English. In French, we call it effet d'aubaine, where, so take the example of old car technology, right? They were small vehicles, but they consumed a lot of gasoline, and we figured out to make super efficient engines, gasoline engines, but now the efficiency we might have gained in terms of consuming less gasoline is spent by one, the fact that we can go faster and farther with those vehicles, and they're massive compared to the original cars in terms of weight, so you need more gas to move them anyway. So that the advances you made by saving gasoline with your gasoline efficient engine are totally deleted, if you will, by the fact that you've added, weight and distance to what you could do with this vehicle. And are you not worried that if we make super efficient devices, let's say, my phone becomes like a super efficient phone, aren't you worried I'm going to make sure that I get more memory and I'm going to get a bigger screen? Like manufacturers are not going to say, wait a minute, I'll use this and I'll keep the prices where they are because now it's cheaper to get the thing to work with a lot less energy. That's a question I worry about. It's like you guys work for efficiency, but manufacturers are just going to make it faster and bigger, aren't they?
Yeah, so there is always in terms of how it is being exploited, right? So because we are driven by science, we are driven a lot by, so there is a lot of the scientific integrity. So we are looking a lot into advancing science and knowledge, while there may be from the industry, a lot of it is cost related, right? So how big is my system? How fast does it compute? What is the tag price? So also what would be, the market, the potential interest. So indeed, the constraints are different, but the transfer, so from a scientific development, so from research and development all the way to this market to have the product and the people that will exploit it, I think the changes that we are making inherently, they will, for the user perspective, they probably might not even realize what type of processor it is, but they will see that it is a faster, so it is much more compact, it can do many more functionalities. They'll see the added value in terms of price per function or price per memory or frequency, how fast does it operate. So this is maybe what the end user, so the people that us, that you'll be sold to. But I guess your challenge is, even though we are making things faster, still the companies that are the main drivers of the market, but also how things are being publicized and sold. Yes, I agree with that, but I think there are two things. The main challenge is that the technology development we make, it has to it has to give, at least address some of the societal challenges we have now. So right. Regardless of who is the company behind it, now companies are becoming more and more aware of what are the main challenges. So we need to think about the planet. We need to think about recyclability of this electronic system. We need to think about how they are made and how long they operate, or what is their lifetime. So I think now there is this sort of a shift, a green shift, right? A paradigm shift. So I hope over the years this will become even more embedded into the company cultures. So every scientific development that we do toward, why is power consumption an issue, right? So we don't have endless resources, right? So there is, I think, all this technology, research and innovation we are bringing forward will serve toward these societal challenges to be addressed. So I think this is the main message we want to bring out, regardless that there might be Samsung or there might be, IBM or might be someone else exploiting this. I think this is what we are trying to make a bigger mark, or at least the impact. We want to address the societal challenges, digitization of industry, right? Recyclability, AI, embedded AI. What are the solutions? How we are keeping, so it's not about making big companies, richer. It's about challenges that we want to address, which are pertinent for no matter what country in the world you live.
Yeah, and I totally agree with you. And that's why I think that, the change will be brought about by researchers like you, but also by economists and engineers also, who are going to be able to work for companies and eco-design and change the culture of manufacturing just for manufacturing. We really, and I think, the notion that resources are not limitless, is core to this paradigm change. You can fix it and make it more efficient all you want. If somebody behind you at the end of that line doesn't agree to not proliferate the devices, we're still in the same conundrum.
But you need a cultural shift, right? So regardless of the domain, so it's in economics, in finance, if it's in science or academia, and we need a cultural shift. And so I think this is something that has become, I mean, over the years now, we see the impact. We are even, undergoing some of these impacts. So it's important that there is cultural shift happening on every aspect of our society. We cannot turn a blind eye anymore to what's happening with our ecosystem.
You're absolutely right. So I understand you're involved, Aida, a little bit with some European effort. Is it through your projects, the European projects, that you're doing some kind of lobbying, or do you have other activities where you're trying to preach in that direction as well?
So I act as on various entities for European Commission as an advisor, but also what I mean as an advisor on their ICT program. They solicit us as experts, but also to give feedback in terms of what would the new program look like, and what are some of the scientific challenges. So the program have members from academia, from industry, also from startups, from various sort of landscape in Europe, and I am solicited to give my feedback in terms of what are some of the scientific related challenges. And so through these committees I find this is an opportunity to bring forward not only the scientific challenges, but also to kind of bring toward them that yes, this cannot be done standalone or independent. We all are part of this ecosystem. We all have a role to play. So this is where I also where I give my feedback in terms of where is the need of power consumption, where is the problems that we are currently facing, and how this can be we can all be part of the solution. So yeah, I have a role in terms of the European Commission with various committee roles that I play, but also through the European projects, because now I'm an active member. I actually am a scientist where I'm leading one of the projects, Neuron. Now the role there is indeed, so through examples, so through our research, to really have, one-to-one comparison, what is the current state of the art on such processors, and what is the current development that is, what is the added value, the competitive edge of our current technology that we are developing. Now there I can have a more stronger impact, because I can concretely say, this is what we are trying to do, and this is what we are obtaining, and we can be more concrete, or our voice can be more credible in terms of the added value or impact that how much we are saving, what is the order of magnitude in terms of energy improvement. So these are the type of roles that I'm very proactive at the EU level. At the national level, we are starting, at least I'm part of the ecosystem, but on a different topic, on a quantum
national
topic.
level would be, excuse me, that would be France, is that correct?
Yes,
national level.
France level, and also the local ecosystem here on the Occitanie. So I'm part of a quantum hub. So here idea is not necessarily power, but it's also a new computing paradigm. So acceleration. So maybe we'll have a moment to talk about quantum as well.
Gladly. Yes, I want to, so a quick question now, and we'll segue into being a woman in science and the management questions that you're faced with. But I'm sensing that with this this activity, this lobbying activity that you have, that organically comes from doing research and promoting your research within European projects, you're now turning into somebody who's promoting paradigm change politically. And how prepared do you feel you are as a scientist to have a political voice? Is it difficult for you, especially as a woman? Is it a man's world? How do you feel about, look, I'm a doctor in science. I run a team of scientists, and now you want me to be a political animal. How do you feel about that?
Yeah, I think this change in roles comes with, as we become more involved in our science, and we have a very concrete results and points to bring forward. I think this came naturally. For example, the power consumption and energy efficiency. I mean, after a point, this could not just be an article that you submit and you publish and you are done with it, right? It has to go further. So that's why the momentum. So how is the project, right? So these are European level collaborations. How did this come about, right? So by talking with other colleagues, industry, both in academia, about the importance of this subject. And we have very good support, as I mentioned, from some of the top companies in working on this, semiconducting companies, and also IBM. So it's very important to say that this transition, a scientist and toward now advocating to the importance of why we are doing what we are doing, and also being a woman, it came naturally. I have to say that this is a lot of, we are a minority. It's a fact,
yes.
It's statistics. Indeed, there are meetings that maybe I'm the only female scientist, but that's okay. I think as long as we can talk about a subject and we can talk about the importance of the topic, I am heard. I think I can go beyond just my gender. I think maybe in the first 5 seconds there would be a little awkward at the beginning because where are the other women, right?
Right.
But then we can focus the topic about what is important, what's at stake, right? Can we focus on the scientific? And there I am heard because we have concrete results. Yes. We are making an impact on science, and I think that matters. But indeed, we have to do something about having more women on board. There have to be, and that.
So let's use this minute on the podcast to, hey guys, all the ladies at Polytech and other engineering schools, this is a doctor, Aida telling you, get involved, women, and change the landscape. And you've hired women on your team, right?
Yes, I do. Yes, I do. I have both, female and male. So I have boys and girls, and I'm very proud of them all. They are bright. It's about intelligence and bringing, the best into the research. They're bright and they need encouragement. And I think women have not had this mentorship. And I think they need this mentor to see as a role model that this can be done and their voice matters and their voice can be heard. So I hope with my experience that I encourage also other young women to embark on this and to embark on the research and also to go forward in their career, either if it's academia or in industry. But we need to bring that.
Aida, what would be your 1 minute advice to a young woman engineer, for example, electronics, where she looks around and she sees nothing but boys, right? And what would you tell her? She's 20, and she wants to save the world and build the best electronics. What would you tell her now that you know what you know?
I would say keep at it. And she is there. She is unique. She's different. And she has her capacity, intelligence to bring forward. So don't even doubt yourself. Just keep at it and keep moving on. And I would simply encourage, because it's rare, and we need to keep this going. And the thing is, it starts early on, not only in graduate or master, but even early on. We need to have this exposure to science to girls. I think it's very important to see that, everybody can code. Anybody, if you give them a mathematical problem with some experience, they can try to solve and also try to design if you give them the right pieces and nothing to bias them. I think we bias our children so much from the early on that they are somewhat intimidated further when they have to make a choice. So I think it's the struggles, at least the awareness should be start early. But even at our level, in master students, and even how I recruit, or even sometimes even in committees, I always check, who are the other invited speakers, if there are women or not. And sometimes it's even at this day and age, it's sometimes very bothersome to see that there are only male panels. It's not right. There are women experts out there. How could it be that they couldn't find, out of all community, they couldn't find one expert female to talk about it? And they don't understand that the impact is not only on her science, but it's also the message she represents as the voice person on that topic.
Of course.
So I am very sensible of that now. So whenever I am going into some event, I make sure that I'm well represented, but also that I'm not the only female. I think it's very important to also for the organizers. We are in 2020. It's about, we need to have this shift. Science belongs to everybody. Science is not biased. We can talk about science without having to judge one another. So science belongs to us all, and we should be able to talk about it all. So that's why we need this awareness starting, as I mentioned early, but also further in the career. As we go up further, I mean, it gets a very narrow circle, and that's also troubling. So on both sides, early on and also mid-career to further.
Yeah. I think the more we speak about it and call it out the way you're doing it now, I call it out in class too. For example, when in class some of the boys make a stupid joke, I call it out. Say, what you think this is funny? It's not funny, you know. And in fact, you should be a class, which means you're together. And secondly, if there's only one woman, you should help her, you know, gain the space she needs in your group, so that more women come and join those groups. So I think we need to work in early. In school and later in college as well, and in a professional world, it's evident that you have to push. So
yes, sorry to interrupt you. And the institutions have a big role to play on this, right? At all levels of careers. I mean, the institutions cannot be blind to this issue anymore, right? The statistics it's revelatory, right? So I think there is a need also awareness from institutional level, how they also take their decisions, and how, you know, from a simple board meetings, from a simple who is part of, you know, some advisory boards, or from, you know, any simple example, there has to be a participants from both sides, because we need voices to be heard from we cannot hear only the same voice all the time. We need voices to represent the reality. The reality is we are 50-50. We need to listen to the other half. And you cannot ignore anymore the intelligence of the other half. So this is also something to, you know, a message for the institutions as well.
You know, in the States, I worked for different companies, and women, much more prevalent. You know, all throughout the hierarchy, specifically at management level. I don't know why it is that in Europe, which is so far advanced from an intellectual standpoint, I don't feel we've reached that level of inclusiveness yet. Maybe I'm short-sighted. Maybe it's just a cultural, you know, misperception. But in my personal experience, you know, women were much more present in decision-making circles in the States than they're here in Europe. Is this your feeling as well?
Yeah. I mean, having experienced both in US and now in France for many years, I think so too. I can't point out if there is one or two subtle things that stand out, but indeed, it could be maybe because also, you know, the historical or sort of a little bit the cultural background. So maybe there is also something cultural there. In US, people tend to be a little bit more outspoken. Right. Yeah. So that's also there, you know, that brings in, maybe it seems a little bit as abrupt or sometimes a little bit as aggressive, but in the end, things are said and discussed in open, so that this sort of transparency also helps to hash out the problems, while hiding behind the problems might not necessarily be the best approach. So indeed, I witnessed the same thing, but I can't figure it out if it's only cultural or it's also maybe the hierarchical paradigm the institutions have put in place of how to govern themselves, organize themselves. So it could be also on the structure management style. It's a tough one to say, but, you know, being part of an academic environment, I think this is a little bit, I mean, we are minority, but at least the field is a little bit leveled, because it's our scientific merits that is sort of at the front line. But indeed, we need to push further women to take more leadership positions. And also that would be because the investment we do now is also for the future. So it's very important to, I hope, you know, that the institutions also take this opportunity to act upon this very important problem.
Okay, well, I hope my Polytech colleagues and my Polytech students, women students, have heard that call, and I totally second it. Ida, before we talk about the U.S., or at least the spirit of creativity and thinking out of the box that comes from doing business in the States, can we talk about what's next for you? Quantum computing, I think, something crazy like that, right?
Yeah, so indeed, I have embarked on this topic for last year and a half now, and quantum computing it's a completely different paradigm from the classical computing that we know of. So rather than having a 0 and a 1, now we are talking about quantum states, the quantum states that have many more variables. Like you can think of a sphere and you can manipulate the spin of an electron to be anywhere on this 3D sphere. So it's very interesting because you can have a lot more states, just a 0 and a 1, a binary state. So this multiple states that you can get with quantum, it's very, because you can use that now to do computations, right? So the properties of, quantum mechanics can be used for doing some very interesting complex problems, and it can solve these complex problems, which currently we can't with classical machine, and it can accelerate. That means you can really do some parallel computation. So it's very interesting for some of the, for example, applications such as quantum chemistry. If you want to figure out, for example, how molecule will bind with another, or to figure out, for example, how to design a new drugs, or even even though these are long term, but right now we are looking into how can we implement these quantum states? What are the underlying devices, right? So there is a lot of collaboration with IBM in the framework of this Quantum Hub initiative, funded by the region of Occitanie and also IBM Montpellier and University of Montpellier. So the idea here is to look into how can we design these quantum devices to build quantum circuits, simulate them. What would be the added advantage? So how much speed up in terms of performance can we get? And then to go toward targeting a little bit more complex problem. But I have to say, this is not just one person or one team. This is the whole ecosystem. So this is a worldwide quantum computing race, if I may call it so, towards developing quantum systems and quantum algorithms.
Yes,
very exciting.
And so the leaders in the field are do you think the Chinese or the Americans? Who's ahead of the game there?
I would say that mainly are American. So we have IBM with their superconducting type of qubits. Then we have Google with similar type of superconducting. Yep. Then there is Intel with a different technology. Then there is, there are all the top main companies that are in US. Also, the Chinese have their own version of quantum qubit implementation. But this is a worldwide race, right? So also Europe has very well played the role. So they have built a quantum flagship. And also in the new program, they have quantum-related calls, so the program that I've put in place. So it is gaining momentum. And France, believe it or not, for once, we are one of the leaders in Europe as well.
All right.
So this is very exciting because why? We have a very strong mathematicians and math background and knowledge, so computer science and mathematicians and physicists. So it's a very, timely momentum for France to play a role in the quantum initiatives and the quantum technologies. And also IBM has invested, especially it shows with our first quantum hub. So this is also very timely for us here in Montpellier.
So would you say, Aida, this is a good direction for our electronic students or IT students to get in?
Of course. This is another, so there's neuromorphic, AI, design, but quantum computing is also a very exciting field for them to join because you don't need to necessarily have a physics background, right? So we have also put in a flow of modules. So if students are interested to embark on this, they can just get in contact either with me or the Quantum Hub, the IBM Quantum Hub here in Montpellier, because why? There is a lot of need for this creative thinking. We are really at the very start, right? So there is this blank page that is waiting to be written, and we need a lot of new thinking, new algorithms, people that maybe will have some crazy idea what to use the quantum computing for. And this is what we are needing. We are needing people that are curious. I think this is the prerequisite, curiosity and willing to learn. So as long as the students want to do that, they can start with Qiskit maybe from IBM or some a small project or a summer internship type of thing to get sort of a feel, a hands-on on this new topic. And why not? They might become the next quantum engineers. And this is what we need. We need to train the people now. This is a very timely opportunity.
This is perfect, Aida, as a segue to discuss. And we talked a bit about this last time we chatted, but how you view research is perhaps in France or the European approach to research might be a little too constricted or formatted, and people are somehow afraid to get out of that box and come up with crazy brainstorming thinking and crazy ideas. I mean, in my experience, in America, we always made room for sessions, which were called brainstorm sessions, whatever you want to call them, where you take stuff and you throw it on the wall and you see if it sticks. And the perfect illustration of that is Elon's SpaceX rockets, his launchers. They crash and crash and crash and crash until they didn't. Everybody laughed at him for so long. Who's laughing now?
That's right.
So I use this illustration as an example of, failure is okay, and you have to allow periods of work where you are totally creative, unscripted. If you're always scripted, you're basically going to shut yourself down into a mode of repetition, and you're not going to make science or literature or whatever it is that you do advance. And so do you agree with that, correct?
Yeah, I completely agree, and I resonate with that. I think failure is part of innovation. Without failure, you don't learn in terms of what could go wrong, what could you improve, what could you do different. So I think failure is part of the solution, of part of the innovation. And I have to say that, I mentioned earlier, research is something that a lot of sacrificing. We need a lot of thinking, a lot of new way of thinking, and to be resilient, because research it's a long-term investment, right? So you need to kind of ride these waves of ups and downs. By the time you could get something to be, really innovative, or a rupture or a breakthrough. I remember, you mentioned Elon Musk, but there are other. Edison would say, I failed 10,000 times, and I made it to that, final success of the light bulb. So, you could give up after 10, 20, or 100 trials, but keep on going. That is the kind of spirit, the resilience, the kind of the curiosity that drives innovation. And I think, yes, indeed, there is some formatting going on at some educational level, but when you are at a master level or PhD, I think this is where you have some maturity and you can think out the box, because this is where you can be, you can make, a difference, and you can be a game changer. I think this is something that the students need to, we need different thinking. The science needs different thinking. Innovation needs different thinking. So it's not something to look negatively upon. It's actually a very important ingredient toward, innovation and to some new ideas.
But so Aida, how do you implement that in your daily life and with your team? How do you make room for folks to feel free to say some crazy stuff and not feel ridiculed by the others? And how do you build that climate of people going, tapping only in the creative layers of their minds as opposed to the protected layers of their research minds? How do you build that?
Yeah, and it comes with time, but trust, right? So it comes with trust and scientific integrity, trust in mind. So I like to put the main guidelines in the beginning when I start to support or advise a student. I like to give specific guidelines so they kind of have sort of a charted path to begin with, so they don't feel as unsupported at all. But after that first sort of 2-3 months that they have been sort of guided, I let them then to start exploring. I want to know about their ideas. So this is where it comes. It's always a continuing process. I allow my students to always pitch ideas to me. Hey, think about this. So we can brainstorm together.
Cool.
And I think this is I learn from them. They learn from me. This is our role as scientists, and this is our role here in academic environment, to provide this nurturing, scientific nurturing, so people can learn, but we grow with them, so we advance. So it's a win-win. Their success is my success in terms of everything that they, to see them grow. So as an advisor, my biggest moment, or how to say, return of investment, if all I do is to see them after 3 years of a PhD journey, that they started here and they're there. So they have the scientific maturity, and they have their own ideas, that they can, the clarity. And that is the most a satisfactory moment that you can get as an advisor to see them grow as scientists, but also as human beings. So
yeah, they're your babies who come out of the family nest, right?
That's right. To see them grow and to have this scientific maturity, and that comes with time. So
now
I apply this on a weekly basis with their meetings because
cool.
So it's an ongoing process.
Cool. The one thing I would also inject there, if I may, from my perspective, whenever I go interact and teach at LIRMM, I find that, and at Polytech, I find that the biggest issue is the French in general, and Europeans really, except for the northern country people, don't like to speak, and they're not comfortable with that. And I think that people at your level with your teams should encourage folks. I assume people speak English in your team?
Yes, they do.
So I should encourage folks to stand up, in front of a whiteboard and start sketching and presenting their ideas, to feel good about speaking, and most importantly, sharing. Because the French will present stuff, but it won't share. And that's what I'm working on with my student engineers, like share your enthusiasm, share it, make me feel what you feel. Otherwise it won't work,
That's right.
That should happen also, in research with people like you who are able to convey that.
Yeah, the sharing and creating this environment where everything they said, it's fine. Nobody's going to judge. Nobody is looking to count points. That this is about a common goal. And I think taking yourself out of this equation that you're going to be judged or scrutinized, because that's why people don't share, because they feel they're going to be judged, right? But creating this environment, that's okay. You learn from it. Even maybe, I did this last week, maybe I tried and it didn't go. That's okay too. So I think we need to create this environment that it's okay to fail. It's okay sometimes to also change things because you learned along the way. So creating this safe environment in terms of people, students are here to learn. If they knew what they were supposed to do, they would go make money out of that knowledge. So I think this is the most important thing. We are here to make them also to grow, but also more importantly, to learn them how to think and learn how to also present that, to share that. So sharing is a key ingredient to success as well.
I agree. I totally agree. And I think that's where our background, our US background intersects. So now I have one last, not crazy question. It would have to do with how you look upon the future. I don't know if you have kids. I have kids myself. And I worry about climate change quite a bit. And that's why I love talking to people like you who are using their job to change things, as opposed to just doing their jobs, to bring about a paradigm change. Do you worry about, the next few decades for the young people who are going to be our age or your age, next few decades? Do you worry about the climate, the, pandemics or fires, whatever, disruption in the food chain, oil supply ruptures?
Yes, a lot of the environmental.
Okay, so I'm saying all those events. Do you worry about that, or do you try not to worry? What's your relationship with what we feel is going on, but we can't quite grasp?
Yeah, I mean, we are all very active on this, all right? So in our communities, for example, I'm part of, it's not a big initiative, but at least in my local community, I'm part of the, how we can recycle. So even with the children at school, when it comes even from how we recycle pencils, right? We should do that, so maybe it's not a big impact, but,
Absolutely.
It starts at school level. It starts to the message to children that we don't just throw things on the trash, right?
Correct.
Even though they are, maternelle, so they are very young, but just to kind of get the idea that we need to give this, we need to make them proactive. They need to be players, right? You need to get them involved. I think this is, so once you make somebody responsible of their actions, then they will try not to disappoint you, right? So this is why the message we need, at least I feel like I'm passing to my own kid, but also to my students here, and also in my communities, get involved. I think that's the, and yes, I'm worried about the long term, because maybe the world or what we went through as children and as young adults may be somewhat different for our children and for the next generation. So it's important not only to leave a good world to them, but they also are good citizens in the world. So there is a two-edged sword, right? So we need to also how to teach them to be good citizens, so to be proactive, to have all of these as I mentioned, from recycling, from how they use, so to be conscientious of how they consume. And also wherever they will go into their activities is to play a role, to be involved. I think this is something that at least I find it very important, because when you give them a task, they try to go through with it.
So our students, our engineering students and your PhD students, what can they do in practical terms, in your view, to impact change? What should they do? Like, what would you say if you had a 20-year-old daughter at Polytech? What would you tell her to do to carry out that mission, that particular part of her life?
So to get involved on there are various different activities, maybe going at the University of Polytech, to get involved and to take responsibility in different levels. I mean, of their involvement. So I think for the main message for the young students is, of course, to continue on, to have a dedicated field or topic that is exciting for them, to continue on embarking on that field, but also to be involved. They are part of a larger ecosystem, so they cannot think that their voice or their role doesn't matter. It's like the voting. Every vote counts, every role counts, everybody's counts activities. So get them involved, get them to be part of the various levels initiatives. Here at LIRMM, for example, we have a green initiative that we have started. And it starts from basic things, from the way how we print, from the way how we use the electricity at day and night, from the way how we even, have our virtual meetings in terms of what softwares, every level there are decisions to be made. So there are, opportunities for young students to be involved. And if not only at their university, at their local. So get them involved. They have to be part. They're all part of the solution, right? We are all part of it.
Yes, get involved and think out of the box. I like those messages, Ida. Thank you very much. I think we've covered the bulk of the things I wanted to ask you. What I'd like to do, though, Ida, is, if you agree with that, is maybe we can meet again in a year or two and see, and do a checkpoint Polycast and see how far you've gone, and if you've changed your view on things, and if you've managed to convince people at the European level, and if you're happy with all that, if you've gotten a quantum computer maybe from IBM for Christmas, something like that.
All right, would love to. Yeah. Thank you for having me. And of course, we can have another checkpoints over the years. It would be great.
Cool. Well, thank you very much, Ida. It was a pleasure talking with you. Keep up the good work, and especially the enthusiasm you bring to your work, and the way you're channeling all your personal strengths to inspire other people. That's really super cool. So take care, and I'll see you later.
Thank you. Thank you.
Bye-bye now.